Okay, so this problem will look similar to when we did inclined plane problems because you're going to have an inclined plane, and then you're going to be breaking some of those vectors into their components. So the reason why we have a bank curve type of problem is because if you're driving on the highway, usually they bank the curve. And they bank the curve so that it gives you something else that prevents the car from sliding off the road when you're changing direction. So what I've drawn here is I'm doing a very general, like the general information that you would know if you were doing one of these problems. So one of the variables that would be involved is the angle. So you could be given the angle of the bank, or that could be the unknown. Most of the unknowns in this problem, most of the variables could be the unknown in the solution to the problem. So when I'm drawing this problem, I'm going to be drawing the back of the car because we're not looking at the car. So that is the rear of the car. So I'm not looking at the car moving down the hill. I'm looking at the car staying at that level on the hill and changing direction. So my two directions in this problem are going to be the centripetal direction because the center of the circle is over here. Okay, the car's changing direction. And perpendicular to that is the y direction. So the y direction is straight down. So you're going to have the weight straight down in the problem. And I'm not going to be breaking the weight into its components. If this was an inclined plane problem, I would actually be taking the weight and breaking it into its component that's perpendicular to the hill and its component that's parallel to the hill. But the weight is all in the y direction, and I'm now, instead of having my directions be perpendicular to the hill and parallel, they're going to be in the centripetal direction and the y direction. And there is a z direction, which would be like into the board, and that would be like if the car was speeding up or slowing down. So that's the first arrow that you want to put on the picture. Now, if this car moves at all, we're trying to prevent the car from moving up the hill. If you're changing direction and it's sliding, it would slide up the hill. So friction is going to oppose that motion. We're hoping it opposes that motion so we can change direction. So the direction of friction in this problem is going to be down the hill. So that's the direction of friction. And so labeling that, that's going to be your friction. Now friction is not in the centripetal direction and it's not in the vertical direction, so I have to take the friction and break it into its components. So I'm going to take that friction and break it into its centripetal component, which would be that, and I'm going to break it into its y component, which would be that. So I'm going to label these. That's going to be the y component of the friction, and this is going to be the centripetal component of the friction. Any questions with this so far? Now, the other force on this picture that I haven't put is the normal force. And the normal force is always perpendicular upward from the surface. So the normal force is going to be in that direction. All right, that is the direction of your normal force. Well, just like friction, the normal force has to be broken into components because I have to break it into its centripetal component and its y component. So I'm going to have the y component is going to be like that. And its centripetal component is going to be like that. So those are the two components of the normal force. So I want those to be labeled. So this is going to be the normal force. Whoops. The normal force is centripetal component. And the other one is going to be the normal force This is y component. I'm sorry, what am I doing? So this is going to be the normal forces y component, and the other one is going to be the centripetal component. Now, if you look at the picture, if I know this angle here, then I know this angle here, because that's horizontal, that is parallel to that, so you pretty much have alternate interior angles. Whatever that angle is, that's going to be the angle right here, so I'm going to write that in. So that angle right there is also going to be the angle of the curve, the bank curve. Now, if you look over here, well, I know that's perpendicular to the hill and that's parallel to the hill. So I know that this angle and this angle, they add up to what? 90. So they are complementary angles. So these two are complementary. And then if I look at this and this, so if I look at the centripetal component of friction and the y component of the normal force, they also add up to 90. So these two are complementary. So if these two are complementary and those two are complementary, two angles that are complementary to the same angle are congruent. So if that's theta, this is also theta. So I can put that in also as theta. Now that's your picture. Now, as soon as you have the picture, the next thing you would do is you would draw your descriptive equations. So if I sum up my forces that are centripetal, I have two of them. I've got the centripetal component of friction and the centripetal component of the normal force. So I'm going to add those here. So they're going to be centripetal component of the force, positive because it's to the right. And I'm going to have the normal force, the centripetal component of the normal force. And when I add those together, they're going to equal mv squared over r. Well, or mr omega squared. Now, if r is the unknown in this problem, and what I mean by the r would actually be the distance from here to wherever the center of your circle is. What I mean by the center of the circle is if I'm on a highway and I take an exit ramp, I'm changing direction gradually, and there's some center of that circle because I'm moving through some fraction of a circle. Now, if I'm on a city street, driving at much slower speeds, I can actually have my streets perpendicular to each other because I'm going so slow that when I change from going, let's say, north to going east, I can do that very quickly, which means it's a very small radius of my circle. I can very quickly change direction from north to east. When I'm on a highway, that change in direction is more gradual. Let me try and show it from above. I'll show you the picture what I mean by above. So if I had, this is the highway, and the exit is going to be, the exit is going to be like that. It's going to be a gradual change in direction. So the radius, what I drew up here as the radius, is on this picture from there to whatever the center of the circle is. So, you know, that could be 30 meters, 40 meters, because what we try and make happen on a highway is when the car is moving here, it may be, you know, maybe down here it's going 60, 70 miles an hour. When it gets here, we're going to start to slow down because we want to take the exit. So maybe when I hit here, I'm going about 40. Maybe I want to get it down to about 30. So I want to, if I'm going 30 miles an hour, I need enough centripetal forces so that it changes the direction. So in the example over here, I'm getting my centripetal directions, because I'm on a hill, I'm now getting a component of friction that's helping me change direction, and also a component of the normal force. So the angle is helping me because it's not that easy. It's harder to slide uphill than to slide downhill. So that's why we bank it. So that when you're in your car, the driver's side is higher than the passenger side when you're taking the exit. All right? Everyone follow that? So let me get rid of this. All right, so I'm at 10 minutes. I'm going to finish the equations and then I'll stop it. So if I finish the equation that I had here, and again, I'm going to use mv squared over r unless r is the unknown. Anything can be the unknown, but I'm going to say in this problem, r won't be the unknown. When I sum up my forces in the y direction, you can see there are 3 forces in the y direction. This one is up, that one is down, and that one is down. So the only one that's up is this one, so that's the only positive one. These 2 are negative. So in writing that, I'm going to get Fny minus Fy minus W equals 0. So what I have on the board is the end of the physics in this problem. The rest is math, because I've got everything that I need to solve this problem. Now, like I said, anything can be the unknown, but the variables that will usually be involved in this kind of a problem are going to be, maybe they'll give you the mass, maybe they'll give you the velocity that the car is moving at, maybe they'll give you the r, which is the radius of the curve that the car is moving on, maybe they'll give you the angle, and maybe they'll give you the mu. So those are really the variables. I want these 2 equations to be written in terms of these variables because these are the things that might be given to you in one of these kind of problems. So one of these would be the unknown, and then the rest you would know. Well, if you look here, not a lot of them are there. Like, I don't know what FC is, I don't know what FNC is, I don't know what FNY is, and I don't know what FY is. If I know the mass, I can probably get the weight. Well, I can get the weight. So I'm going to actually do a couple more, knowing what my definition is for friction and knowing that I can use trig to get components, I'm going to be replacing these 4. Okay, so I'm going to stop here with this podcast and go to the next one, because if I go beyond 15 minutes,